introduce Professor Andrei Andreevich Shkalikov from Moscow State University. He will speak about half-range problem in operator theory.
Okay. Maybe better from here. Many thanks for the introduction, and certainly I'd like to start my talk from thanks to the organizers for inviting me to give here 45 minutes lecture. It's a great honor, and I thank very much, certainly personally, Skobachevsky and all organizing committee. Skobachevsky explained the importance of this conference, that it is already a traditional conference and attracts a lot of very good mathematicians. The only lack, the only shortage of this year conference is that we have a lot of conferences simultaneously. In particular, we just came from St. Petersburg, and we are now in Rudan University, and parallelly, simultaneously, we have a conference in Suzdal, organized by Davidov. Certainly, in future, we should take into account these circumstances and to divide, to just take care that conferences have to be organized not simultaneously. So I will speak about half-range problem. The translation of this talk should be проблема половины в теории операторов. This subject is, at the moment, it is not very popular, I would like to say. So, I mean, in Russia, not very popular. Actually, in the West, and in the East also, this topic is rather popular. I will try to explain what does it mean. Certainly, I will speak about some new results which I obtained just recently, but it is not written completely at the moment. But my goal at this lecture just to give representation, what does it mean, half-range problem. What's going on? How to? Does it work? Maybe. Okay. So I will tell about 3 stories, and it will give representation. What does it mean, half-range problem? First story is about invariant subspace problem. You know that it is very difficult problem in operator theory, and you know that famous mathematician Per and Floor proved that in Banach space it is there are operators which have no non-trivial invariant subspaces, but in Hilbert space this problem is not solved. We don't know if an arbitrary operator in Hilbert space possesses an invariant subspace. However, this problem certainly important. I mean, the problem, invariant space problem in Hilbert space, but much more important problem, which I will tell now. Let us consider Hilbert space and introduce indefinite scalar product, like it's written here, where J is involution operator, self-adjoint, and the square of this operator equals identity. It's just for convenience. Actually, we can consider any self-adjoint operator which certainly bounded, because with unbounded metric we will have too much trouble, and it's also convenient to assume that this operator is invertible. Otherwise, the metric, indefinite metric, is called non-regular, and also we will have too much problems. In very natural way, we can define self-adjoint operators in Pantryagin and Crane space. I can tell that if the rank of operator is a P minus or P plus is finite, say kappa, then this space is called Pantryagin space, and if both projectors P plus and P minus are have infinite rank, then it is called Crane space. And in natural way, we can define self-adjoint and dissipative operators in Crane space or in Pantryagin space, and maximal dissipative operators. It means that operator equivalently maximal dissipative if JA is dissipative and there is a point mu in C plus in the right half plane, such that mu belongs to the resolvent set of JA. Assume that A is decomposed and represented is as operator matrix. I wrote here A11, A12, A21, A22. It means not every unbounded operator can be represented in such a form. However, if its domain can be decomposed, can be decomposed into D plus and D minus, where D plus and D minus are defined as the intersection with H plus and H minus, then such representation, I mean matrix representation, is possible. And now we have problem which the so-called invariant subspace problem in Crane space, that does a self-adjoint or M dissipative operator A in Crane space possess a maximal non-negative A invariant subspace. Certainly we can, the indefinite scalar product is defines quadratic form, and there are subspaces where this quadratic form is negative or non-positive, positive or non-negative, and we can define the so-called semi-definite subspaces. Semi means either they non-negative or non-positive. And if such a subspace does exist, then the question is either the restriction of A plus into this invariant subspace has the spectrum only in the closed half space C minus. And if yes, then for application it is important, does the operator A plus, this restriction, generate a strongly continuous semigroup or holomorphic semigroup? These three questions are of interest in this theory. It turns out that invariant subspace problem in crane space is unsolved. It is open. It is open problem, and at the moment there are no ways how to approach the proof of this problem. And just historical remarks are the following, that first, in the case kappa equals 1, so if we have only quadratic form has only one negative square, then the problem was solved by Sobolev when he investigated the problem of rotating top with liquid which is filled by a liquid. This investigation was not open and was published only in 1962. But a few years later, Pontryagin proved that if we work in Pontryagin space, it means that P plus or P minus, the rank of this operator is equal kappa less than infinity, and then there is a maximum non-negative invariant subspace with dimension exactly equal kappa, such that the spectrum of the restriction A until A lie in the upper half place. Please excuse me, sometimes I will speak about right half plane, sometimes about upper half plane, because I just follow the works, the work of Pontryagin dealt with respect to the upper half plane, some other works, so it depends certainly on the test of order. Then a similar theorem was proved by Crane, also in the space P kappa, but he dealt not with self-adjoint operators in Pontryagin space, but with unitary operator. But certainly by Kelly transform you can come from one to the other. But what's important that the proof was different. It used fixed point theorems, quite nice and quite short, because the proof of Pontryagin was it was a big paper, about more than 25 pages. I don't remember exactly how much. Moreover, Crane applied his results to the stability problem of equations of with periodic Hamiltonians, and he proved that the equation is stable if and only if the Monodromy matrix for this equation is the unitary operator in P kappa. What and the equation is stable if only if all the eigenvalues on the unit circle are of definite type. But actually, I will not. I don't have too much time to define what does it definite type, and it's very easy. Vector is positive type is this quadratic form, indefinite scalar product with this vector is positive, and so the definition is very natural. Then after these results, the student of Langer, the student of Crane, actually he is German mathematician, and now he works in Vienna, in Austria, and but he was the student of Crane, and he generalized this theorem for operators with matrix representation. It's better maybe if you have matrix representation A equals A11, A12, A21, A22, then he proved that invariant subspace problem is positively solved, provided that this operator is compact, this operator is bounded, and certainly all these operators are bounded, because at that time there were no papers which dealt with unbounded operators. Crane gave another proof of this result, but fixed point theorem, it was not Bauder fixed point theorem. He used Schauder-Tichot fixed point theorem. So the generalization of Bauder fixed point theorem gave the same results as proved Langer. Crane-Langer algorithm in 1971 up to 1980 proved generalized these results for self-adjoint operators for dissipative operators in Crane space. Just in few minutes I will tell about my results in this topic, but just now I'd like to tell a little bit about other results in this theory. So the main developments in this theory were this compact operator A12 and with the so-called definite non-negative operators. With operators which satisfy this inequality for all x in the domain of operator. In this case, Langer worked even with unbounded operators, and he proved that any self-adjoint operator possessing such a property does have invariant subspace, which is non-negative. Moreover, non-negative and non-positive, the so-called dual pair. Then he developed a theory which is written in very huge papers, and not too much understand actually this paper, but actually he developed analog of spectral theorem for self-adjoint operator. He developed for self-adjoint operator in Crane space. So I told already that he proved the existence of a maximal dual pair. And then Dirichlet proved that any bounded non-negative operator in Crane space possesses this property if A is non-negative, but B is from Neyman-Schatten class, the class of compact operators which are a little, I will not explain what does it mean, but they are a little bit better than, it's very easy to define lambda k, if lambda k are denoted by, the eigenvalues are denoted by lambda k, then the series lambda k to the power p converges. In this case, we say that B belongs to SP. If we have this perturbation, then certainly, not certainly, but A plus B has invariant dual pair. But open problem, which is challenging, but I did not succeed to prove this at the present moment. If this result is still true, provided that B is not from Neyman-Schatten class, but just simply compact operator, it would be, I do believe that it is true, but at the moment it is not. About continuation of Crane-Langer invariant subspace problem. I'd like to present my results here. So we, as before, we have operator A, which is which can be decomposed as operator matrix. As before, we have fundamental symmetry, which is defined by this operator, and H is H plus and H minus, and H plus is the space where X operator A11, no, and usual representation. Assume that GAB dissipative in H. Let the following conditions hold. Three conditions. First, A22, this operator, is maximal dissipative in H1. So it means that A22 minus mu exists in the left half plane. Operator F mu, the resolvent A22 times A21 admits a bounded closure for some mu in what does it mean? It means that A21 is subordinated to A22. Means usual subordinates is if you have this nth order differential operator, the same or maybe degree of A22 must have not more than the order of A22, not more than n. And the most the main assumption that A12 has to be not only subordinated to A22, but compactly subordinated. In this case, we have there exists a maximum non-negative A invariant subspace, and if GA is M dissipative, then among these subspaces there is a subspace HL plus, subspace L plus, such that the restriction of A plus A operator onto invariant subspaces plus lies in the closed left half plane. Actually, this result was proved by myself in 2007, so 15 years ago. But now I can prove more. It's not written up to now, but the main result is actually the following: that under assumption of the theorem which I formulated, the operator, the restriction A plus, generates a holomorphic if this operator A11 generates a holomorphic or strongly continuous Riemann group of excuse me. Actually, I can present several additional assumptions when A plus generates a holomorphic strongly continuous or holomorphic semigroup of exponential type 0. In particular, if this operator generates a holomorphic semigroup, then so does A plus. This restriction, which is guaranteed by this theorem. So I tried to tell about first story invariant subspace problems, and this is one of the topic which belongs to the topic which I called half-range problem. Another story 2, concern factorization theorem. I'd like to start with secure theorem. This theorem asserts that if we have the function f on the circle, which belongs to L1, which is summable, then it can be represented as the modulus of a function g, which belongs to the Hardy class. So in particular, it is square summable, belongs to the space L2 on the circle. This is true provided that we have this condition. Actually, generalization this theorem to the matrix case was quite dramatic. Zasukin, the student of Kolmogorov, announced this result for matrix case, but he died during the Second World War, and later Kolmogorov learned that Crane knows the proof. He invited his to the meeting of Moscow Mathematical Society. Crane presented his proof, but he didn't write it. Actually, his students just tell many stories that quite often Crane presents the results, but didn't write down all the proofs accurately. So the proof was published by Rozanov, the student of Kolmogorov also, Simultaneously, it was proved by Norbert Wiener and Mazzani. From the circle to the complex plane, it was translated by Ackezer. Then Goldberg, Arrow, Laudenswager, Devinat, Douglas, Rosenblum, not Grigory Rosenblum, but another Rosenblum in the United States. Yes. Ravnyak, Matsayev, they also were occupied with this topic. And from this topic, we can, in particular, get that quadratic operator pencil with bounded, with bounded self-adjoint operators P1 and P2, provided that it is positive on the real line. Admits factorization, and moreover, there are many factorization of this form, but there is Z such that its spectrum lies in the lower half plane. Again, I'd like to say a little bit about other problems which are here. You see, if you have here strictly positive, then certainly, and consider the quadratic form P lambda XX. Certainly it is lambda minus P minus X. This is quadratic usual scalar polynomial, lambda minus P plus X. Certainly, both roots of the scalar quadratic equation will be in upper half plane. So it is so-called elliptic case. But in contrast with this case, if we have that the real roots of this quadratic polynomial are real for all x's, then it corresponds to the hyperbolic case. And in this case, for matrix quadratic polynomial, Dashin proved the factorization, and the generalization of Dashin theorem was Crane-Lange theorem that in strongly hyperbolic for strongly hyperbolic pencils, we have factorization the same, and Z and Z1 are operators which are similar to self-adjoint operators. It is certainly important. What means strongly hyperbolic? It means that the spectral zones P minus, when X runs through the whole space H, P minus runs through some segments, finite segments A minus, B minus, and P plus also fills in the segment A plus, B plus. So if the distance between first zone and the second one is positive, then such pencils are called strongly hyperbolic. For strongly hyperbolic pencils, there were a lot of results, not only for quadratic but also for polynomial ones. In particular, theorem of Langer. And as for me, I just to mention is that in 1988, I investigated the case of hyperbolic pencils, not only bounded but unbounded too, which when the zones attach each other, not strongly but just usual hyperbolic, and found not necessary but sufficient conditions which are close to be necessary when operators which participate in factorization actually similar to self-adjoint operators. And also I gave some applications to some problems which were considered by Wadizhins, by Kapilevich and some other mathematicians. Okay. Now I'd like, I thought about elliptic pencils, hyperbolic pencils, now about problems of mixed type. I'd like to ask chairman, not chairwoman, how much minutes I have. 9 minutes, okay. Quite important results was proved by Crane and Langer, and what's interesting that they discovered the connection between invariant subspace problem and factorization problem. It was certainly this paper by Crane and Langer had a lot of subsequent papers. So they considered quadratic pencil and proved the factorization provided that C is positive, and they proved, certainly for bounded operators, they proved the factorization with operator Z, which is K, now C 1/2 square root of C, with K less or equal 1. And the idea of proof that they reduced pencil to the operator at matrix of this form, it turns out that this matrix inherited spectral problems of the operator pencil of Landau, and then using invariant subspace theorem, they proved that there is maximum non-negative subspace with K, which is contraction, and but we have invariant subspace if and only if we have operator Z, which satisfies this equation. This is a particular form of the so-called operator Riccati equation, and from this Riccati equation, factorization actually follows, because if you substitute instead of Z operator K C square root of C, which satisfies this equation, then automatically we will get factorization. A lot of literature was after this problem, and in particular, I had results for unbounded operators, not only for, but with some restrictions which sometimes they do. We can improve these restrictions, but sometimes not. Now my results about this subject. In the case when we have elliptic pencil, and not only, no, in this case, let it be bounded operators, self-adjoint bounded operators, but I assume that C is compact operator. Then we get factorization, but in contrast with Crane-Langer theorem, I have here K, not contraction, but unitary operators. It is quite important. Then continuation. Continuation is the following. Let we have here, before we had lambda square plus lambda b plus c, but now I wrote in with R and T, where T is self-adjoint, but R is symmetric with domain which is equal or larger than the domain of T. Assume that we have a point on the real axis such that this pencil is strictly positive. Without loss of generality, we assume that this point is 0. Otherwise, we shift the parameter spectrum. And assume also that T minus 1 is compact. Then, if we have the estimate of resultant, for the system of elasticity, for Maxwell equations and so on and so forth, this condition is abstract Agman-Nirenberg Agranovich condition for elliptic system. So if we have elliptic system, then on the real line we have this estimate, and provided we have this estimate, we have factorization. We have factorization as before with operator Z, which is equal K square root of T, where K is bounded and boundedly invertible. Certainly not unitary, because in this case we admit that on the real line, we can have eigenvalues. The assumption that T is compact guarantees that the spectrum of operator pencil L of lambda is discrete. In particular, on the real line, we have finitely many eigenvalues, and we can assign, either positive type or negative type to the eigenvalues which belong to the real axis. And I can guarantee that this operator Z will have the spectrum in the upper half plane, but on the real line, only those eigenvalues which are of positive type. In this case, if these eigenvalues are simple, it means that L prime of lambda k, yk, is positive. And this operator, this quadratic forms plays a role of energy functional. So there's a connection with concrete promises which have important implications in the wave guide domain, wave theory. Factorization of the pencil implies factorization of the equation, and in this case we can prove that the solution which corresponds to the time t more than 0 do exist, and this solution is unique, and it can be applied to the relay problem, Mandelstam hypothesis, and so on. So I did understand that I will not have enough time to come to the third story. I just say only 2 sentences. Another third story actually deals with self-adjoint operator matrices, and the question is when such an operator matrix admits diagonalization. Not always it is true. It is also connected with invariant subspace problem, with factorization, with all this topic which I called half-range problem in operator theory. Many thanks for your attention.
Thank you very much. Please, questions, comments? Okay, I have a question about compact perturbations. Yes, you say that you can consider compact perturbations from Schatten-Neumann class, but not arbitrary.
Mm-hmm.
And can you consider compact perturbations, for example, from Lorentz classes, SP infinity or something?
In particular from Matsayev class and so on.
Mm-hmm.
No, it is up to now there were more 30 years have passed from the Dirichlet paper, but no results in this direction were obtained. And actually I do certainly I do believe that for the Matsayev class it can definitely it is true, but it's also true for arbitrary compact operators. But at the moment, to be honest, I tried to manage with this problem and to solve it, but my efforts, I did not succeed.
Thank you. Any other questions? Please.
I ask some more general, perhaps, question. We know that in not in operator case, but in
matrix.
Not even in matrix, but for there is a Gauss theorem for when you have not pencil but arbitrary equation of n type and it has n roots in complex space.
Okay.
Can we expect some type of this theorem in operator form, and where does this old subject come from? Is it some problem in, for instance, physics or somewhere application? Do we have some expect some application of this general results?
Very good question, but it's not easy to answer this question. Certainly, there are applications, but up to now, we don't have books where all these problems are written in details. Concerning your first question, I can tell the following. Not only quadratic pencils, but pencils of arbitrary order. In matrix case, though it is investigated by a number of mathematician leaders were Gogberg, Rodman, Lancaster, Kashuk, and I can tell many. They wrote a lot of books. But all these books dealt only with matrix case. Certainly, it's very restrictive. You can, using, say, Galerkin method, you can consider models which approximate your real problem in the matrix case. And then these results can be applied. But in infinite dimensional case, if you go, you meet a lot of really difficult problems. And up to now, you see, in 90s, I get some results, some applications for relay problem, for Mandelstam, for elasticity theory, but under some restrictions. For example, for elasticity theory, I had restrictions for parameters, lambda mu, which are involved in this equation. Now I try to get rid of this. I did succeed, but actually there are a lot of questions which I don't know how to solve. But I'd like to say that's true. Application, a lot of applications, but in infinite dimensional case, results are difficult.
Thank you very much again.
Thank you.
We have 3 minutes break. Okay, let's continue. It's my pleasure to introduce Professor Crasta from Rome, and he will speak about concavity properties of solutions to Robin problems.
Thank you very much, and I'd like to thank the organizers for inviting me here. It's an honor for me to be here, and I also like to thank the staff of this conference, because they have done great work and they are still doing a great work for keeping all running smoothly. So I'm going to talk about concavity properties of the solutions to Robin problems. I'll mainly focus on the first eigenvalue of Robin problems, and the results that I'm going to discuss are obtained in collaboration with Ilaria Fragala from Politecnico of Milan. And this is a quick outline. I start just introducing some basic notation. So what concerns the eigenvalues of the Laplacian operator, and the fundamental gap. Fundamental gap is just the difference between the first two eigenvalues. And then I'll try to show you how to estimate from below this fundamental gap. And I'll try to show you how what's the role played by the log concavity of the first eigenfunction when trying to get this estimate. Then the known estimates are for the Dirichlet Laplacian, and then I'll discuss what happens when in the case of Robin boundary conditions. And here I'll discuss some negative and some positive results, and then in the end I'll just discuss some open problems. So let's start with basic notation. In this talk, omega will always be an open-bounded connected domain with sufficiently smooth boundary. I'm going to discuss this later. It is well known that for the Laplace operator, or even for more general operators, with different kind of boundary conditions I'm going to discuss in a moment, the spectrum is purely discrete. That is, there is an increasing sequence of eigenvalues that here in my notation they can be repeated when the eigenspace has multiplicity bigger than 1. And then here I'll denote, so this lambda j denotes the eigenvalues, the increasing sequence of eigenvalues, and by phi j I'm denoting the corresponding eigenfunctions. Here I'm considering two types of boundary condition: the usual Dirichlet condition, when we require our solution to vanish on the boundary of our set, or the Robin boundary condition. Here this denotes the outer unit normal to the boundary of omega. So Robin conditions is of this kind. We have here the normal derivative of the solution plus a fixed parameter that in my case will be always non-negative times our solution equal to 0. So here we are mixing in a linear way the boundary value and also the value of the normal derivative. You see here that when beta is equal to 0, we have the usual Neumann condition. And so here we can think of this Robin condition when beta goes from 0 to plus infinity as a sort of interpolation between Neumann condition for beta equal to 0 and Dirichlet condition that, okay, here only heuristically, you can see that we can think of Dirichlet condition when here beta is going to plus infinity. Okay, so there are two very basic but fundamental questions. Okay, here I just recall that lambda 1 will then is always the first eigenvalue, and this difference, lambda 2 minus lambda 1, is what is called the fundamental gap. It's the first gap in the spectrum. And there are, I was saying, two main questions. One concerns the simplicity of the first eigenvalue. What the simplicity means that the corresponding eigenspace is one-dimensional, and estimates from below on the fundamental gap. Both problems are very important. Yeah, I just quickly discuss a very basic setting. For example, if we are interested in studying the asymptotic behavior of the solution of the associated parabolic problem, as t goes to plus infinity, we can expand our solution using eigenfunction and eigenvalues in the usual way. And then we see that e2 lambda 1t times our solution can be written as a constant times the first eigenfunction plus this other series that we can see as a reminder. And we see that if the first eigenvalue is simple, then this left-hand side is converging to a multiple of the first eigenfunction. And an estimate of on the fundamental gap, so an estimate on lambda 2 minus lambda 1, is giving an estimate on the rate of convergence to 0 of this reminder. This is a very basic setting, but these estimates on the fundamental gap are of huge importance also in physics, in statistical mechanics, quantum field theory, for the control of error in numerical methods, for refined Poincare inequalities, and so on. There are at least 600 or 700 papers, recent papers, for the majority in the physical literature that use this estimate on the fundamental gap in various contexts. Okay, I'm not going to discuss the simplicity because in this setting it is well known that the first eigenvalue is simple for the Laplace operator and also for more general uniformly elliptic operators. I just say here two words just to self-cite myself here. That simplicity has been proved also for some nonlinear operators, such that the P Laplace operator, or also its game theoretic version, which is the normalized version of this P Laplace operator. And so I would like to focus on the fundamental gap estimate, which is directly related to the concavity result. So, so here we are considering the Laplace operator of also Schrödinger operators of this form minus Laplacian plus a convex potential, but with Dirichlet boundary conditions. So Andrews and Clutterbuck proved in 2011 this fundamental geometric estimate. If omega is a convex, so a bounded convex set, then we have this estimate which is independent on the potential, and so it's a purely geometric estimate. So the fundamental gap is estimated from below by 3 pi square, and here at the denominator we have the diameter of omega squared. And up to 2011, this has been known as the fundamental gap conjecture, because it was conjectured in the 80s, but because computations on parallelepipeds or sets like that just give this condition, but it was proved only in 2011. And this estimate is indeed optimal. We can approach this estimate for flat potential, so for a constant potential, and in dimension 1, this is an equality. You can just do the direct computation. In dimension bigger than 1, this is a strict inequality, but this bound can be reached just, for example, using a sequence of parallelepipeds with one side of fixed length and the other side with length going to 0. So thin parallelepipeds. And these estimates, optimal estimates, improved the already known estimate by Yue Chong without these 3 here, and a previous estimate by Singer, Wong, Yao, and Yao, which doesn't have these 3 here, but and with the 4 at the denominator. So now I just want now to consider the case of Robin boundary condition. So here we have omega convex, beta positive, we have our eigenvalue equation, Robin boundary condition. Even with Robin boundary condition, the first eigenfunction does not change sign. So from now on, I always assume that it is positive in omega. And I'd like to show you that if we assume this is the essence of the proof of Yue Chong and also of Singer, Wong, Yao, and Yao, if the first eigenfunction is log concave, that means its logarithm is a concave function, then we can get this estimate. This is the estimate of Yue Chong, but indeed, in this case, we can't get a better estimate independent of beta, because this is the optimal estimate for Neumann boundary condition. So here, for beta equal to 0, here we have Neumann boundary condition, so we can't get a better estimate independent of the parameter b. Instead of the Laplacian, we can consider also more general Schrödinger operator with a convex potential. Okay, thank you. So I just would like to show you how the log concavity of the first eigenfunction plays a role in all this stuff, in all these estimates. So here is the essence of the proof of Yu and Chong, and after also of Andrews and Clutterbuck. If we consider this function v of xt, which is this ratio, here we have e to minus lambda 2t phi 2 x, and at the denominator we have the similar quantity for the first eigenvalue and the first eigenfunction, then it is easily seen that this v, this function v satisfies this parabolic equation. Time derivative of v is equal to the Laplacian plus a drift term, which here we have a vector field, capital X, which is 2 times the gradient of the logarithm of the first eigenfunction. Here we have the scalar product with gradient of v. And this function v satisfies a Neumann boundary condition on the parabolic boundary. This is true both for Dirichlet and for Robin boundary conditions. Then you see in a moment that if the logarithm of phi 1 is a concave function, then its gradient, here capital X is 2 times its gradient, satisfies this inequality. This is the inequality satisfied by the gradient of concave functions. And then in this situation, Andrews and Clutterbuck have shown that we can indeed give an estimate on the modulus of continuity of this function v, the modulus of continuity with respect to the the space variables for every fixed time t. And more precisely, this modulus of continuity can be estimated by the modulus of continuity of a scalar function phi. Here phi depends on one space variable s, which lies on the segment 0 d over 2, where d is the diameter of omega. D will always denote from now on the diameter of our set, and t is the time variable. So if we can find a function phi of two variables, two scalar variables, such that its time derivative is greater than or equal to the second derivative with respect to s. It's increasing in the space variable. It's non-negative for s equal to 0 and for every time, and such that at time 0 provides a modulus of continuity of the function v at time 0, then this function phi at every time t provides a modulus of continuity for the function v at time t. But now this function phi can easily be found just solving here equalities, and indeed it is not difficult to see that for every positive constant c, this function, here you see we have a constant, here we have an exponential with this important constant, which is pi 2 over the diameter squared of the set. And here we have this sinus, sine function. This function satisfies the first three conditions here. And indeed, at time 0, this function phi is c times this sine of pi s over d. And if we choose c big enough, then at time 0, this function phi is a modulus of continuity of the function v at time 0. Function v at time 0 is nothing but the ratio of the first two eigenfunctions. And so, estimating, if we estimate the oscillation of the function v at time t with the oscillation of the function phi at time t, we get this inequality that must hold for every non-negative t. And here you see that if you let t go to plus infinity, this constant here, lambda 2 minus lambda 1, which is the fundamental gap, must be greater than or equal to this constant here, which is pi square over d square. And so we get the estimate that we were looking for. So you see that here the only ingredient in this proof is the log concavity of the first eigenvalue. This log concavity under Dirichlet boundary condition is well known, at least since the fundamental paper of Braskamp-Lieb in 1976. And just an additional comment to get the estimate, the optimal estimate for Dirichlet boundary condition, Andrews and Clutterbuck have modified this proof in order to take in account an improved log concavity estimate that I'm not going to deal with. Okay, before going ahead, I just want to mention some other contribution to concavity. I just cite here the concavity maximum principle by Korevar, then the continuity or the formation method by Caffarelli and Friedman, the constant rank theorem by Korevar and Lewis. By the way, I'm going to use these two results the following slides. And then there is a very huge bibliography here. I just cited, I just wrote down Caffarelli and Strack, Kennington, Cavol, but there is a long list. In more recent years, there are also contributions for fully nonlinear PDEs and for viscosity solution. I talked about these extensions to nonlinear PDEs in my talk of Monday. But there is a bad news. I don't know if there is a problem. Andrews, Clutterbuck, and Auer, they have recently proved that, unfortunately, the first Robin eigenfunction needs not to be concave. And so this proof doesn't work. And I just want to comment on their result, just to give a glimpse on their result. They considered only convex polyhedra in Rn, and in between convex polyhedra, they considered this class of product of circumsolids that I'm going to denote by this P. And okay, a circumsolid is just a polyhedron such that there is a ball which is tangent to all its faces. For example, these three here are circumscribed, are circumsolids in dimension 2. And a product of circumsolid is just a Cartesian, let's say, a Cartesian product of circumsolids. For example, this last solid here is the product of a regular pentagon with a segment. Okay. And they proved that if omega is a convex polyhedral, then and if omega does not belong to this class, that is, it's not a product of circumsolids, then for sufficiently small values of beta, the Robin ground state is not log concave. Here the proof is very technical. The paper is more than 40 pages. But in the end, they proved that the logarithm of the first eigenfunction can be written as beta v plus a small error in beta, where v is the solution of this boundary value problem. And they show that this function V is concave if and only if omega belongs to this class. So if omega does not belong to this class V of product of circumsolids, then V is not concave. And so you see here that if beta is small enough, also the logarithm of psi 1 is not log concave. And this is not a problem which is due only to the profile of the function phi, because also the level sets of the first eigenfunction are not convex for sufficiently small values of beta. And there is not a problem of regularity, because if we approximate a set, a polyhedral set which does not belong to this class with a smooth set, which is sufficiently near the polyhedral in the Hausdorff distance, then also for this smooth set, the corresponding first eigenfunction is not log concave for small values of beta. Clearly, this result leave open this conjecture that they wrote on their paper, that is, for large beta, for large values of beta, one can expect that the first eigenfunction is log concave. Why one can expect this result? As I have said at the beginning, the Robin boundary conditions in some sense are interpolating between Neumann boundary conditions and Dirichlet boundary conditions. Dirichlet when beta is going to plus infinity. We know that for Dirichlet boundary condition, the first eigenfunction, this is the result of Braskamp-Edip, the first eigenfunction is indeed strictly log concave. So we can expect then we are approaching the Dirichlet case, also the Robin boundary, the Robin ground state is going to be log concave. So we can expect that for a fixed convex domain, there is some threshold, let's call it beta star, such that above this, for beta above this threshold, the Robin ground state is log concave. And if this is the case, it will be of interest how to understand how this threshold depends on the space dimension and on the geometry of the set. And indeed, with Ilaria Fragala, we proved a positive result in this direction. Here, omega is a uniformly convex, smooth domain. What I mean for smooth, smooth means of class Cm with m greater than or equal to 4 plus n over 2. And then for these domains, there exists with a positive threshold beta star, such that above this threshold, the Robin ground state is strictly log concave. In addition, this beta star can be chosen in a uniform way in this class of sets, that is, if we restrict ourselves to a class of uniformly convex sets of class Cn with diameter bounded by some constant, minimal curvature bounded from below by some positive constant. And here, by this delta m, I called this delta m the higher curvature, the maximum of higher curvatures. Without entering too much into detail, we can consider this as a bound on the derivative of local parameterization of the boundary of omega. So we can choose this beta star uniformly, depending only on these three parameters. Okay, I just would like to give a glance at the proof. So, if here I called V1 minus the logarithm of the first eigenfunction, so we have to prove that this V1 is a convex function, at least for large values of beta. Indeed, we are going to prove that the Hessian matrix of V1 is positive definite in omega. And here we use the continuity or deformation or homotopy approach by Caffarelli and Friedman. And this approach consists in deforming our set into a ball via a regular deformation. Here the deformation is constructed in this way. We just consider for t in 0, 1, let's say the convex combination between a fixed ball B and our set T. So for t equal to 0, we have the ball. For t equal to 1, we have our set omega. I'm denoting by phi t the first Robin eigenfunction in omega t. This phi t depends only on the parameter. Depends also on the parameter beta, but I'm not writing it just to keep the notation light. And I'll denote by Vt minus the logarithm of phi t. So we are going to prove that the Hessian matrix of Vt is positive definite in omega t for every t in 0, 1. In this way, for t equal to 1, we get our proof. And how does it work, this method? Okay, for t equal to 0, we have the ball, and so V0 is the ground state in the ball. This can be explicitly computed by means of Bessel functions on this stuff, and indeed it is its Hessian matrix is indeed positive defined. Now, the idea is starting deforming our set, so our parameter starts from 0, then is going to 1, and we are looking what happens when we vary our parameter from 0 to 1. And we need basically two ingredients. The first ingredient is consists in proving that this Hessian matrix is positive definite near the boundary of the corresponding set. So we have to prove that for every t, this Hessian matrix is positive definite near the boundary of omega t. This is a highly technical point, and I'm going to discuss this point in the next slide. So let's take this point as given, and then we start with the deformation process. So we assume by contradiction that the claim is false. So we start with our V0, which has a Hessian matrix positive definite. We start deforming. If our claim is false, that is, if it's not true that for every t we have a positive definite matrix, we can find, let's say, a first time when our Hessian matrix fails to be positive definite in all of the omega s. And we can compute the gradient and the Hessian matrix of our Vs, and it's simple to see that the Laplacian of Vs satisfies this equation. Here you see that we have first eigenvalue, which is positive, plus this non-negative quantity, which is the square of the norm of the gradient. But here plays a role the constant rank theorem by Korevar and Lewis, because if we have a positive, if we have a C2 function with Hessian matrix matrix which is positive semi-definite, and which solves this equation. Indeed, they considered also more general equations, but in particular this equation. Then the Hessian matrix has constant rank in all the set. But we said here that this Hessian matrix has full rank, has maximal rank near the boundary, and so it needs to have maximal rank in all of omega s, and so it is positive definite and not semi-definite. And so this is the essence of the deformation method. Okay, let me say some words about the first point, which is the most technical one. We achieved this result. We have proved that this Hessian matrix is positive definite near the boundary by comparison with what we already know in the Dirichlet case. Okay. In the Dirichlet case, we can perform explicit computations which can't be done in the Robin case. And indeed, we have a first theorem which says how our Robin eigenfunction and eigenvalues are near the corresponding Dirichlet ones. Here, this superscript D denotes the quantities related to the Dirichlet case. So this inequality says that the distance between the Robin eigenfunction and the Dirichlet eigenfunction in the C2 theta norm is bounded by a constant over beta. So you see this goes to 0 in a controlled way as beta goes to plus infinity. And a similar estimate can be done also for all the eigenvalues. Here, what is important is that these constants depend only on the geometric quantities that I have described before. That is diameter, the minimal curvature, and that's bound on higher curvatures. So, in the class of sets that I have defined before, these constants can be chosen in a fixed way. Another technique, okay, you can just don't try to read this estimate. This is, you can see this is a boundary estimate for the gradient of the first Dirichlet eigenfunction for the ground state. And okay, the ground state in the Dirichlet case, we know that by Hopf's lemma that has a non-vanishing gradient on the boundary, but here we need a precise estimate on this gradient, and we got this estimate which depends only on okay, this estimate is valid on convex sets satisfying a uniform interior sphere condition. Okay, so it's valid for C2 sets. And here you see that this estimate from below depends only on here this row. Sorry, I have not written. This row is the radius of the interior sphere condition. Here we have the diameter, and here we have other constants depending only on the, on the radius of the set and the radius of the interior sphere condition. And okay, this result is technical. Again, we have proved it thanks to a suggestion of David Jerison by using an Harnack chain of balls, and a recent estimate of the hotspot. The hotspot is the point where the first eigenfunction achieves its maximum value. And there is this recent estimate on the position of the hotspot. This says that the hotspot cannot be near the boundary with these precise estimates. Then there are also a lot of other technical points that I'm not going to discuss, but in the end, using all this stuff and comparing with the Dirichlet case, we have proved that indeed this Hessian matrix is positive, definite, near the boundary of omega. For every beta greater than or equal to this threshold, and this threshold is going to depend on these three quantities, which are the quantities that I have, the geometric quantities that I have defined before. The first Laplace eigenvalue, the first Dirichlet eigenvalue, and the Q that I have defined in the previous slide. But in the end, okay, the problem is that we have to keep this beta star controlled during all the deformation process. Because, okay, for every t, we have a beta star depending on t, let's say. But we have to guarantee that when t is going to 1, this beta star is not going to plus infinity, for otherwise we don't have a threshold for the final set. But indeed, using the ingredients that I have described before, we can see that indeed this beta star can be uniformly bounded from above using only the three geometric quantities that I have defined before. So I think I have 4 minutes, something like that. Okay, thank you. Okay, but I have almost done. I just want to mention that using almost the same techniques, we can prove a concavity result also for the torsion problem. That is, torsion problem, what is the Robin torsion function is the unique solution of this boundary value problem. That is, here we have a fixed constant, let's say 1, and here we have our Robin boundary condition. In case of Dirichlet condition, it is well known that the torsion is 1/2 concave. And indeed, we proved that this is the case also under Robin boundary condition in the class of sets that I have described before. And here we use almost the same tools that I have already shown. Let me quickly discuss some open problems that we have. That we have no idea how to solve them. We have tried, but without any result. The first problem concerns the regularity assumption. We are considering only CM sets. It would be of interest to understand what happens for non-smooth convex sets. For example, the basic example is the case of plane triangles or circular sectors in dimension 2. But we have no idea of how to proceed. We have tried, but without any result. And another interesting question is this one, to characterize the convex domains for which we have concavity for every value of the parameter beta. What I mean, for example, in the case of circumscribed polyhedra, we can conjecture that we have concavity of the first eigenfunction for all values of beta. That is, we have a result only for large beta. There is some evidence, there are a lot of sets where you can perform an explicit computation where you can see that you have concavity for all values of beta, but we do not have any idea on how to achieve a result like that. And then this is a somewhat unrelated problem, but it is related with my talk of Monday. What about other kind of inequalities? I'm mainly interested in the Minkowski type inequality for the first eigenvalue of the Laplacian under Robin boundary condition. So I think my time over. So I thank you for your attention.
Thank you very much for very interesting talk. Are there any questions, comments? You talked about estimates for the Schrödinger operator on a bounded domain.
Yeah.
That is some force potential minus Laplacian.
Mm-hmm.
But which class should this force potential belong? Must it be smooth or just continuous, or maybe summable function will qualify?
There should be C1 convex, a C1 convex potential for this result, just in order to write. It also for continuous convex potential, I think. I don't remember exactly this point.
The potential must be convex.
Yes, the convex, or it must satisfy some form of weak convexity, some weak form of convexity. Let's say convex. There are results also for potential which are convex with respect to one direction. And there are many variants, but since in this geometric estimate we are not really interested in the potential, because we are giving an estimate which holds for all potential, for all convex potentials, and the optimal estimate is approached when the potential is indeed constant. So anyway, you need, for this kind of estimates, you need convexity, or at least some form of, let's say, weak convexity.
Thank you. Are there other questions?
By the way, you can find a deep discussion in this in the paper of Andrews and Klapperbach.
Are there such results about Laplace or even trimal Laplace in on manifolds? For instance, yes.
There are estimates on the fundamental gap on manifolds with positive curvature, or with the first estimate in let's say in a non-flat case have been obtained on a sphere. But then there are also, I have seen papers with estimate on manifolds of positive curvature.
Okay, thank you. Some other questions? I have one question.
Yeah.
So this bound that you prove is independent of beta,
Yeah.
for any beta. But probably for large beta, it must
Sure.
be, the bound must
Sure.
be better.
Sure. Indeed, we have a partial result in this direction. We have proved a bound with the optimal bound minus a part which depends some fixed constant and the part depending on beta and which goes to 0 in beta. But indeed, we have, it is not an optimal bound, but indeed is a better bound, at least when beta is going to plus.
Thank you very much again. And it's my pleasure to give certificates. Please, Andrei Andreevich Shkalikov and Professor Crasta, please.
Thank you very much.
Yes, thank you. Now we have a coffee break.
Добрый день. Сергей Борисович, вы нас слышите? Сергей Борисович, у вас выключен микрофон.
Ну вот, да. Алло, слышите меня, да? Слышите?
Да, замечательно, слышим вас, видим. Вот, мы можем пока, если хотите, попробовать, ну, пока здесь перерыв, ну, расшарить экран, посмотреть, что все хорошо.
Давайте расширим, вроде как такого.
Ну, это есть.
Ну, давайте так вот. Ну, я думаю, что вы видите сейчас, да? Вы сейчас
Да,
видите.
я видим.
Ну, все, я его сделаю, Ctrl-L, все будет хорошо. Ну, все тогда, собственно, сейчас его закрываю, да, или как мы это делаем? Как,
Да.
или можно оставить даже, что с ним делать?
Ну, как хотите. Если хотите, я могу вас сразу вывести это, ну, на экран. Ну, еще вот 10
давай.
минут.
Вообще 10 минут. Ну, кто хотя, собственно говоря, ну, можете выведем, пусть по себе будет на экране, почему нет?
Хорошо.
Так, тогда я сейчас его делаю в полный экран, full screen. Вот, full screen, да, все, сейчас я вижу, что страница перематывается.
Вы должны тоже видеть это у нас на камере.
Что? Ну, сейчас я вас не вижу, потому что у меня full screen, это же, к сожалению. Ну, вроде как оно, может, важно. Может, и не важно. Вот, ну как, так что у нас осталось 8 минут. Что-то, хорошо, 8 минут.
Ну, все хорошо,
да, хорошо, вы можете так, все, я уже включен, я тут сижу, никуда не ухожу.
Хорошо, спасибо.
Да, не за что. Good, so I'm back.
как нам появился Сергей там на...
Все, вот я.
Ага. Wait a minute.
I will now... Сейчас.
Слышно меня?
Да, вас слышно, я сейчас должен снова показать вам, да. У меня был...
Вас почти не слышно. Можно как-то... Я вот к нашим техническим работникам обращаюсь, чтобы как-то громче сделать.
Сейчас.
О, лучше.
Угу.
Добавили громкость. А так, куда он исчез? Угу. Так,
экран вы видите?
Все отлично. И экран видим, и вас вы показываете, и вас видим даже.
Ну, даже это может лишнее.
Почему ж?
Вот все.
Так, значит, давайте продолжим нашу сегодня утреннюю секцию. И у нас докладчик Сергей Куксин с докладом Kolmogorov theory of turbulence and rigorous theory of one-dimensional turbulence. Okay, unfortunately, the talk of Sergey will be online, but this is usual now. Okay, you can start, Sergey.
Так, ну хорошо, то есть мне очень приятно выступить на этой конференции. So, good morning, and доброе утро, and добрый день to everybody. Do you hear me, by the way? Because I hear nothing right now. Excuse me, do you hear me? I don't understand what is going on. Do you hear me? Do you hear my voice or not? Hello?
We can hear you well. We can hear you well.
Okay, хорошо. So I continue. Now I cannot. Okay, fine. Actually, my talk is based on a recent book with Alex Borishev, who was my PhD student, and this book is based on previous papers of my own and of previous papers of my good PhD student. One of them is Alex Borishev himself, who is now in the University of Lyon, and another is Andrei Biruk, who is now in the University of Krasnodar. Actually, I gave a number of talks on this book already, but the field is rather big, and every time I'm trying to change something in my presentation. So even if somebody heard this talk already, I'm pretty sure that he will find something new in this version of the talk. A part of the book, I can recommend my review paper with this title, which is easily available on the internet, which is Kolmogorov theory of turbulence, blah blah blah. Okay, so firstly, what does it mean, Kolmogorov theory of turbulence? The Kolmogorov theory of turbulence was created by Andrei Nikolaevich Kolmogorov in 3 short papers published in the year 41, and therefore it carries the name of the K41 theory because it's the year 41. Of course, he used some results of previous researches on the field. Most of all, the work of Jeffrey Taylor and of von Karman-Howard. But his insight to the theory and his contribution to what was known before was really very big, and so probably now Kolmogorov theory of turbulence is the most popular and in the cleanest theory of turbulence. Despite this is a heuristic theory. So creating it, and Andrei Nikolaevich Kolmogorov worked as a physicist and not as a mathematician. So Kolmogorov theory of turbulence is, as every theory of turbulence, deals with velocity field u of tx of a fluid, or of a gas. We assumed that the units in which we measure velocity are chosen in such a way that this u of tx is a quantity of order 1, and just to make the field more treatable and easier, we just assume that all velocity fields which will appear in my talk are space periodic of period 1. So that is to say that they just X is a point of three-dimensional torus, and three-dimensional torus, and this is three-dimensional torus of period 1. If so, then among the main parameters which characterize flow of fluid, only one parameter remains free. This is viscosity of the fluid. Therefore, Reynolds number of the fluid, which equals to mu to minus 1. If somebody does not know what does it mean, Reynolds number, it doesn't matter, so he can take this as a definition of it for the purposes of my talk. And turbulence, this is something which happens with the velocity field when the Reynolds number is very big. This is to say when the kinetic viscosity of the fluid is very small. So the parameter nu is crucial for me, and everybody always in my talk I will stress dependence on nu, and therefore all constants which appear in my talk will be independent from nu. So dependence on the viscosity nu always will be clear. The message which Kolmogorov made in these three his papers is the following: that the short scale in X features of the turbulent flow u of tx of a fluid, short scale means something which corresponds to short increments of the space variable x. So this short scale phenomena display a universal behavior which depends on the particularities of the flow only through very few parameters. In my setting, all these particularities of the flow depends on the situation or through only one parameter, viscosity. This is because I suppose that the flow is space periodic with period 1, and this is because I have chosen the units in which I measure everything, such as the velocity is a quantity of order 1. Right. So the Kolmogorov theory of turbulence is statistical, but the statistical and just probabilistical language which I will use in my talk will be minimal. In any case, it means that the velocity field u of tx depends on the random parameter omega, which depends on which belongs to the probability space omega capital. Moreover, Kolmogorov assumed that the random field u omega of tx is stationary in time and homogeneous in x. It means that statistical properties of the velocity field u of tx and of shifted velocity field where c1 and c2 are constant. Statistical properties are the same. If for somebody what I have just said about homogeneity are not clear, this is not important, because later I will use just minimal usage of this homogeneity. So as I hinted before, the main object which Kolmogorov studied and just examines are just increments of the velocity field, where the size r of the space increment is quantity which is small but not very small. I will explain later on what does it mean. So what does it mean small? It's clear, but just it should be a small number, for example, definitely smaller than 10 to minus 2. And what does it mean that r should not be very small? I will explain later. Similar, Kolmogorov studies behavior of the Fourier coefficient. This is notation of the Fourier coefficient for the vector field u of tx, and he studies second moment of the Fourier coefficients as a function of s. And again, when he is doing this, he examines this for the size of Fourier coefficient s, which are big but not too big. And again, I will explain later what does it mean. What does it mean not too big? Since, as I said, writing his three papers, Kolmogorov worked as a physicist and not a mathematician. then in these works he never refers to specific equations of motion of fluid, which should be responsible for the laws which he describes. He uses only just very basic and very general properties of solids, like dimensional analysis like this. But later, when people started to think how one can try to prove Kolmogorov's law, it behaves more or less consensus later in 60s and 70s of last century that the right equation which should be corresponding to the Kolmogorov theory of turbulence, this should be three-dimensional Navier-Stokes system on three-dimensional torus, stirred by random force of order 1. And this random force of order 1 as a function of smooth variable should be smooth. This is unfortunately so the business of rigorous justifying of the Kolmogorov theory of turbulence, for example, based on the Navier-Stokes system with random force, for the moment seems to be absolutely impossible. It seems that for the in future, not maybe just for 10 years, this cannot be done because we have to achieve some much deeper understanding of complicated nonlinear partial differential equation compared to what we have before. Fortunately, Kolmogorov theory of turbulence admits a one-dimensional model. This one-dimensional model is given by the stochastic Burger's equation, which is something like one-dimensional Navier-Stokes system with a random force, and this one-dimensional stochastic Burger's equation is described by a fictitious one-dimensional fluid which doesn't exist. But despite this one-dimensional fluid does not exist in physical realities, at least no reasonable physical realization of one-dimensional fluid seems to be known yet. The results of studies of this fictitious one-dimensional fluid are popular. People are doing this starting from late 30s of last century, and very often the obtained results they give good indication of what really happens with three-dimensional fluids. The comparison which I like is the following. So just hopefully everybody who listens to me, he knows that the three-dimensional elasticity theory is now essentially the branch of partial differential equation, and this is a rather complicated topic based really on deep facts from partial differential equation, and thick books are written to present three-dimensional theory of turbulence. Still, one-dimensional Hooke law, which we learned in high school and which is about elastic springs, it gives really very good insight on the elastic behavior of solid matter, and so gives good insight on what does it mean real physically realistical three-dimensional theory of elasticity, right? So this is roughly the relation between one-dimensional fluids, fictional fluids, and physically real one-dimensional three-dimensional fluids. So the goals of my talk is the following. I will formulate one-dimensional versions of the Kolmogorov claim. I will prove them, or rather discuss how to prove them, using the one-dimensional model given by Burger's equation. And after this, I will discuss real three-dimensional Kolmogorov claims, because after this it will be easier to explain the meaning of the Kolmogorov laws of the theory of turbulence. And doing that and taking Burger's equation as a model for one-dimensional turbulence, I will follow Burger's himself, Uriel Frisch, and just most of all Yakov Sinai. Okay, so now this is Burger's equation. The equation himself without the force, this is just Burger's equation. This so unknown is function u of tx. T is bigger than 1, x is space variable, and as before, I suppose periodic boundary condition. Nu is the viscosity, and nu is always bounded by 1, and it's always positive. Also, I specify initial data u0 and x. Now this is very easy exercise to check that if u0 of x and if the force is there should be psi, sorry. And if the force psi is such that the mean value of the force equals to 0 and the mean value of initial condition equals to 0, then our solution, then the solution of this equation is such that its space mean value also is 0. Therefore, I'm always talking about solutions in forces such that the mean value in x equals to 0. Right? Right. Next, here in this setting, the right-hand side it has this form of time derivative of some function c of tx depending on a random parameter, and just I will assume as it traditional, as for example was done in papers by C9, that psi of t omega is a Wiener process in the space of functions of x. What does it mean? In the space of periodic function on S1 of 0 mean value, I pick up a usual trigonometric basis which denote ES. For positive S's, these are cosine functions. For negative S's, these are sine functions. So altogether, this is a trigonometrical basis in the space of periodic function with 0 mean value, and I can decompose psi of tx for a fixed t in this basis. This is the decomposition. Right, and in this decomposition, Bs's, the real numbers. I suppose that the real numbers decay with S. In particular, that the very important for me quantity Bs is finite. Therefore, at least we deal with two function. In fact, I will always assume, at least for the purposes of my talk, that these numbers decay to 0 even quick. That Bs decays to 0 faster than any negative degree of S, right? And also I assume that here Bs omega of t for various S, these are copies, these are standard independent Wiener processes, right? So Wiener process is something of order 1, Bs, which are real numbers which are quick decay to S. Therefore, for every fixed omega and for every fixed values of t, psi of tx is a function of x, is a smooth function of x. It's a function of t, it is just continuous. Therefore, in the right-hand side, we have a time derivative of a function which is continuous in t and smooth in x, but it is not a big deal. It is not a big deal before, since, okay, so this, what I, just a bit more. That for every omega, the function psi of tx defines a continuous curve in any Sobolev space Hs. This is more or less what I said. Since this is true for every S, it means that psi as a function of t is continuous and as a function of x is smooth, right? And then, since we have in the right-hand side time derivative of something, then I understand solution of this equation in the integrated sense. So U is a solution of Bureaucracy equation if integrated version of the equation holds for every moment of time. And then it is a relatively easy exercise for everybody with some experience for nonlinear partial differential equation, that for every psi omega of tx like this equation has precisely one solution. And this solution is again a continuous function which is continuous curve in every Sobolev space HR. This continuous curve depends on the random parameter U omega. And then the logic of the theory of turbulence is the following. So what should we study when we work with the theory of turbulence? The answer is the following. We have to consider various functionals f, which is a functionals defined on a function space of function of x, right? For the specific values of t, we consider f of u of t. This is a number, and then we have to average this on the random parameter. It is the same equivalent definition is written here. So on physical language, this is an observable. So this is what physicists see and in performing various experiments. And this is the observable averaging ensemble. because averaging in omega, this is what they call this is what they call ensemble averaging. And this is what we have to study, and this is what we have to understand, how to examine these quantities for various functional f's. This is the goal of physical analysis of this equation and of their solutions. Accordingly to what was said above, I will regard solution u of tx of equation b either as a random field, that is to say a function of tx which depends on the random parameter omega, or as a curve in some functional space, for example in L2, which also depends on the parameter omega. That is to say as a random process in some space of function of s, for example, as in the function L2. Well, I will soon explain that in average solution u of tx of Burger's equation, no matter how small is positive nu, stays of order 1. You see, for any nu, if I examine L2 norm of solution, and if I consider squared L2 norm, and if I take expectation of the squared L2 norm, I will obtain a quantity of order 1. And this happens uniformly in values of time, which are just separated from 0. And what is remarkable, uniformly. Since the order of magnitude of a solution u naturally can be defined like this as a square root of the expected value of the squared L2 norm, then the solutions are quantities of order 1, and they have space period of order 1. So this is how we should normalize solution of three-dimensional motions of fluid in the first page of my talk. So in accordance with what on the first page of my talk, so then the Reynolds number of solution u of tx of the equation equals to nu to minus 1. So Burger's equation with small nu describes one-dimensional turbulence in this fictitious one-dimensional fluid, which Uriel Frisch called turbulence. So now, more specifically, my goals are the following. Study solutions u omega of tx for small values of viscosity nu and for all values of t, maybe even up to infinity. So then examine what happens when t goes to infinity, right? Because turbulence, this is what happens when Reynolds number is very big, that is to say when viscosity is very small, right? And we relate the obtained results with the K41 theory regarding Burger's equation as a model for one-dimensional turbulence. Well, I should say that inspired by the heuristic work on the stochastic Burger's equation by just Uriel Frisch. With collaborators, Sinai with his three collaborators in the year 2000 has written this well-known paper which was published in Annals of Mathematics, which increased interest of mathematicians for the stochastic Burger's equation for a model for one-dimensional turbulence, and what is also important for me, and what in big extent motivated the presentation of the result, which is made in our book and which I now follow in my talk. Our approach is different from the approach which Sinai took in his paper. I will explain what is the difference. And our approach allows to build a rigorous theory of one-dimensional turbulence, that is to say turbulence, similar to K41. And in particular, our results will rigorously justify the heuristic theory of turbulence built in well-known among physicists paper by Uriel Frisch and collaborators, which is now 30 years old. Right. So since I want to examine non-linear equation, that is Burger's equation with small viscosity, then of course, as everybody who is working with non-linear PDEs knows, I should start with a priori estimates for the solutions for the Burger's equation. And then the first and the crucial result is the remarkable inequality, remarkable Alleinik maximum principle for solutions of Burger's equation. Olga Arseniyevna Alleinik, she obtained the estimate below for solution for Burger's equation with a smooth right-hand side. But for solutions with the right-hand side, her proof can be repeated with a relatively small modification. So repeating the argument of Oleinik for solution for Burger's equation with a free random parameter, and then averaging the obtained estimation parameter, we arrived at the theorem which is given below. This theorem is as you'll see, this really remarkable result. Unless you knew it, you should be surprised. Result is the following. For any initial data U0, for any positive P, for any viscosity nu, let us also take a threshold theta, where theta is any positive number smaller than 1. Theta for me is a threshold in time. I will consider values of time only bigger than theta. So time will be only bigger than theta. Then I do the following. I consider value of my solution at time t. I take L infinity norm of solution. I raise it to degree p. Then I consider derivative ux of solution. I take L1 norm of derivative. I also raise it to degree p. And I take expectation of this object. Then expectation is bounded by absolute constant c times theta to degree minus p. Here's the whole point that this constant c depends only on the random force. Remarkably, it doesn't depend on the viscosity nu, and it doesn't depend on the initial data U0. So this is absolutely remarkable result, and I'm trying to guess how Olga Arsenina felt when she saw this estimate, and how many times she checked her calculation to see that it's really correct. This remarkable estimate is extremely powerful. Right. Then you see, then everybody with experience in nonlinear PDEs knows that if we have a priori estimate for L infinity norm of solution, we can iteratively estimate Sobolev norms of solution. And then doing that and just arguing when people always use, when they wish to estimate higher Sobolev norms of solution iteratively. And yes, so this is without any special trick. We can estimate for any m, for any integer m, Sobolev norm number m of solution. And the result is the following. If I at any moment time t, which is again bigger than theta, it should not approach to 0, right? I take squared Sobolev norm number m. I will take expected value of Sobolev norm number m. That this expected value is bounded again by a constant, which depends only on m, only on this threshold theta and on the random force, but now times nu to negative degree, nu to this negative degree. For m equals 0, this estimate is not true, because for m equals 0, beta estimate follows, beta upper bound follows from Oleinik maximum principle. It should be right upper bound follows from Oleinik. It should be just a constant as the right hand side. So this is just, as I said, there is nothing special in this estimate, because for many other equations, if we have an estimate for L infinity norm of solution, we'll get estimate like this. What is remarkable in Burger's equation, that in the sense which I will explain very soon, this estimate is sharp. This estimate is sharp, so it cannot be improved. So this exponent is sharp, and so this is crucial. This crucial fact which allows the progress in Burger's equation, which I will explain. Okay, so now to explain why this estimate is sharp, let us use the balance of energy relation for the solution of Burger's equation. Look, if I consider solution of Burger's equation at some fixed time t plus sigma, then this quantity which is here, this is average kinetic energy for solution. Average kinetic energy of solution for Burger's equation at time t plus sigma. Now let us consider the increment of the average kinetic energy from time equals to t capital to time equals to t plus sigma. Right? Then the following well-known balance of energy relations hold. for deterministic Burger's equation and for deterministic Navier-Stokes equation, if we have zero right-hand side, that we have the same relation with zero in the right-hand side. If in stochastic Navier-Stokes equation, if in Navier-Stokes equation or in Burger's equation, the force is a smooth function which is deterministic, then in right-hand side we will have integral of L2 scalar product of solution at time t with a force at time t, which is not so convenient, which is a quantity not explicit. But it is a remarkable feature of the stochastic forces which I use, that in stochastic setting for stochastic forces, the right-hand side is this number, which is simply proportional to the length of the increment of time. And here B0, this is a quantity which is something like roughly squared at L2 num of the random force. Here is the definition of the B0. Now let us assume that in this relation t is bigger than 1. Then Aleynik maximum principle with t replaced by t applies. Therefore, due to the Aleynik maximum principle, this quantity is bounded by some constant c star, and this quantity is bounded by a constant c star, right? Now let us choose sigma. Sigma in the right-hand side so big that sigma times B0 is bigger than 4 times this constant c star. If so, then this object is smaller than 1/4 of the right-hand side. This object is smaller than 1/4 of the right-hand side. And the consequence is that the third term is bigger than half of the right-hand side. This is what is written here. This is what is written here. Right? If it is bigger than half of the right-hand side, and this gives me a lower estimate for the H1 norm of solution, but locally variation time. You see. So this is for any fixed S, this is precisely squared at H1 norm of solution. Then what I do? I locally average in time this H1 norm of solution, and I take expected value. And we have this estimate. Now let us introduce some notation. For any random process, that is to say for any real function f of t, which depends on random parameter omega, I will denote by double brackets the averaging of this random process in ensemble and local averaging in time. So this is the definition. And I will always assume that in this averaging t is bigger than 1, and the time of averaging is bigger than c star, which was used on the previous slide when I spoke about the balance of energy relation. Then what I have just proved is that squared, that averaged H1 norm of solution is bigger than μ2-1 times constant, right? But by theory number 1, I have upper bound like that. Right? Therefore, altogether, these results tell me that squared H1 norm of solution, averaged in the sense of this double bracket, of double bracket and this, right, is a quantity of order μ-1. This symbol means that if I divide this quantity, okay, this symbol means that left-hand side and right-hand side differs by a constant, by some absolute constant, which depends on nothing, only on the random force. That is to say that if I take this averaged H1 norm squared and multiply it by nu, then this number is estimated from above by absolute constant and is estimated from below by absolute constant uniformly and nu. And also, by the way, uniformly in time t of averaging and uniformly on the length sigma of the quantity. Here we have arrived at the first result, which is postulated in the Kolmogorov theory of turbulence, and which we cannot prove for Navier-Stokes equation, but we have already proved for Burger's equation. Namely, in the K41 theory, the phenomenon, this is just the name, the names are very historical. which is called dissipation anomaly. Anomaly states that for the hydrodynamical turbulence, if I have a turbulence velocity field, if I take h1 Sobolev norm of velocity field squared, and if I average it, that mu times this averaging is a quantity of order 1. Is a quantity of order 1. And here this brackets is a suitable averaging, which is essentially we have some substantial liberty to choose averaging which we like. It may be averaging an ensemble. It may be also averaging an ensemble in time, which as I did. And this quantity of order 1, this is crucial object for the Kolmogorov theory of turbulence. Kolmogorov denoted it by just epsilon, which is rather unusual. Why he did so, I don't know, because you see yes, and this epsilon is a key component of the formulas which are used in the Kolmogorov theory. And you see, so now we have already proved the dissipation anomaly. That for Burger's equation, this quantity is of order 1. Right. Now look, now the result which we systematically use when we worked with nonlinear equation, this is Gallardo-Nirenberg inequality. Simply, the inequality is always written, of course, without averaging. It is written for deterministic function, but I simply claim that after averaging, Gallardo-Nirenberg stays true. And then Gallardo-Nirenberg tells us that if I consider L2 norm of du over dx, then I can estimate it as HM norm of du over dx to some degree times L1 norm over du over dx raised to complementary degree. And these are explicit degrees which are written which were found by Gallardo in Nirenberg. But now watch. But now by Aleynik, the last factor here is bounded by absolute constant. Therefore, we see that the left-hand side is bounded by absolute constant times the averaging of Sobolev norm number m squared. This inequality gives us lower bound for what we have here. Yes, but the object on the left-hand side, by our previous result, is bigger than mu2 minus 1 times absolute constant. Therefore, from here we get that average squared Sobolev norm number m is bounded from below by nu to the degree to m minus 1 right? But before we had get upper bound by exactly the same exponent of nu. So then we have arrived at the basic estimate, which is a key step of our analysis of the stochastic Burger's equation, is that for any initial data, and for any value of viscosity which is positive and smaller than 1, for any m Sobolev norm number m of solution squared it and averaged behave as mu to the degree to m minus 1. And jointly with the Aleynik estimates, this equivalence turned out to be a powerful tool to start the Burgerance. Just since we are here, let me mention an open problem. You see, I have this equivalence, but we do not know if the object on the left-hand side admits asymptotical expansion as nu equals to 0. That is to say, we do not know if for this object holds asymptotical relation like this. This is an open problem which presumably is really complicated. Actually, I am not sure that this is true. This is true, we can prove. But if this quantity admits asymptotical expansion like this, I do not know, and I have no idea how to prove it. Right. And now let us move to the one-dimensional theory, of turbulence. Well, just I recall that we. Okay. Let us consider u of tx solution of the Burger's equation, and now let us simply decompose. Yes, and let us decompose this in the trigonometrical basis as before. This coefficient in this of this decomposition. crucial quantity in the Kolmogorov theory of turbulence, and the basic characteristic, basic number which characterizes solution U of Tx as a one-dimensional turbulence flow is the dissipative scale. This dissipative scale, usual notation is LD, another name is Kolmogorov inner scale, or this Kolmogorov dissipative scale. Kolmogorov dissipative scale. And it is easier to define it in terms of Fourier coefficient. So I defined it as a big number, Very often, instead people define this LD as small number, inverse to this one. So in my definition, this big number is defined such that this is the smallest number of this form as negative degree of mu, such that for values of S much bigger than this LD, the average squared norm of the Fourier coefficient number m decays very fast. What does it mean? First, what does it mean that S much bigger than this LD? It means that let us take S bigger than mu to degree minus CD minus something positive. Then it should be that for S as big as Z, Fourier coefficient number S squared and averaged decays with S is smaller than S to any negative degree minus n. This is you see, so this is threshold after which Fourier coefficient of solutions decay faster than any negative degree. And then our first result concerning turbulence is that dissipative scale of solution is a quantity nu to minus 1. Well, in physicists, okay, and in the Kolmogorov, in the K for the -1 theory, dissipative scale is nu to minus 3/4. As you see, it's very close. And Burgers himself predicted correct value of this scale, which is nu to minus 1. I will skip the slide because I have only 2 minutes left, and this will allow me just to present maybe the most important result of our study of turbulence. Look, a small scale increment is this quantity. So I consider increment ux plus L minus usx, where L is small. Let us consider the piece moment of this small scale increment, and let us average it in everything. Let us average it in x. Let us average it ensemble and locally average it in time. So let us consider this option. It is called structure function. Structure function of a solution U, and the name came from the theory of turbulence. Now watch. If a random field U is smooth, then this should be proportional to L to degree P. For smooth random fields, it should be proportional to the L to degree phi. Right? But now this is again the definition. But now this is the definition. But now what happens for the stochastic solution of the Burgers equation? You see, let me recall you that nu to minus 1 is the inner scale. So Fourier coefficient S with S bigger than nu to minus 1 decays very quick. In the X presentation, corresponding quantity is inverse, is nu. So and then it plays a fundamental role because it turns out that if we consider increments L, which is smaller than the inverse inner scale, smaller than nu, then the structure function behaves as if U was a smooth random field. You see, it behaves as L to degree P. Here we can qualify dependence on U, right? So for very small increments, so for increments shorter than the inverse space scale, structure function behave as if U was a smooth random field. But if we consider increments which are not too short, which are bigger than this inverse space scale, then the behavior is different. Namely, if P is smaller than 1, then indeed SP as before behaves L to degree P. But for P bigger than 1, structure function, no matter how big a PS, behaves as L. You see, this is something very nonlinear. It shows that in fact this is very non-smooth random field, right? Non-smooth random field. Right? And so this is the main result. So now half a minute. So the analogy of this result. So firstly, this relation for increments, space increments, which are not too short, which are bigger than nu. This is main result on the paper of this paper of Frisch with collaborators. And in the Kolmogorov theory of turbulence, the structure function, when we take L bigger than the inverse inner scale, not too small, because for L too small, this is again SP of L because L to the repeat. Yes. Then due to Kolmogorov, the second structure function behaves L to the degree 2/3. This is a celebrated 2/3 law of the Kolmogorov theory of turbulence, maybe the most famous result of the theory, right? And as we see that now for turbulence, S2 function behaves as L. Again, it's rather similar, but very different. We have more results, but my time is up, and this is, in fact, this is the main, maybe this is the main, because this is the main relation of the Kolmogorov theory of turbulence, and this is the analogy of this main relation for turbulence, which is obtained through qualitative analysis of stochastic Burgers equation. And thank you for your attention.
Thank you, Sergey. This is the end. Yes, you finished.
Yes, I have finished. My time is up, so I finished, yes.
Your time is over, that's true. Okay, let us thank Sergey Kuksin for a nice talk. Are there questions? Yeah, okay.
The question is not related directly to your achievements, but just of curiosity, because there is some motivation to ask it. What is happening if the viscosity will be a random variable? This question arises in other formulation.
You see, this is of course this is a very good question. Of course, this is a very good question. You see, quite a number of our estimates. It is in fact it is pathwise. So it is very well may be that some non-trivial information can be extracted from our results, because quite a number of our results is pathwise. For example, Aleynik estimates remain true. Aleynik estimates remains true because you see for every yes, it is true. It's true. Aleynik estimate is true because it is proved for every fixed omega for any nu, right? For any nu. So then probably upper bound something also can be done. With lower bound it is much less obvious because we use Ito formula in fact, and I don't know how the balance of energy will look like. So it's definitely a good question, but I don't know much.
Okay, thank you. Maybe it has no physical meaning, but in other problems this appears.
No, it's a nice question. It's obviously a nice question. It's a nice question, yes, but we did not think about it.
Okay, thank you.
Any other questions? Okay, now we have 7 minutes break. Question, please.
Professor Jäger, you're welcome. You can ask a question. Just turn on your microphone.
I very much enjoyed your very interesting lecture. For me, it's very interesting.
Thank you.
And
Thank you.
I have a question. You mentioned that Kolmogorov in the beginning did not look at Navier-Stokes.
No, he did not.
Because when we go to the boundary, That means really when we have flow along a boundary, then the problem is Navier-Stokes will no longer be valid because of the interaction with the boundary. It's a long time to go in this direction, but very important. Can we generalize this approaches to non-Navier-Stokes assumptions?
Unfortunately, I know nothing about this. I doubt. You see, so many times we deeply use specific of Burger's equation. So what happens in this result, which I talked about, it's a small miracle. And it's a small miracle of Burger's equation. So I think that if you replace Burger's by something else, it will immediately fail. It is very difficult to keep this analysis for some other systems apart from Burger's. My collaborator Alex Borishek, he has some examples, but hardly they can be regarded as hydrodynamical examples. So it's a miracle. As I said, this is like Hooke law versus three-dimensional elasticity.
No, but it's
So
is it more a problem being off from the boundary, or it's a problem of dimension?
You see, off of the boundary, do you think off the boundary? So, for example, we can regard your question, what happens if we take Burger's with Dirichlet boundary condition on segment 0,1, right? So if something is interesting happens there at the boundary. But then maybe the Burger's is not a model for fluids at the boundary. You see, even I cannot tell you, we did not think properly. At least I did not think properly for about Burger's on the segment 0,1 with say Dirichlet boundary conditions, right? And even if we could, so then I doubt that it is a good hydrodynamical model. So the answer, I know nothing. More brief answer is that just I know
have
nothing.
to stop discussion because we have only 2 minutes before the next talk.
Okay.
So let us thank again Sergei Kuksin for 2 minutes break.
Professor Golse, hello.
Yes, hello. Good morning. So, close share tray, open share tray. Right. Okay. Let me see. Do you see my screen?
Yes.
So you see the talk now.
Not yet. We can see only your camera.
Mm-hmm. So let me open tray. Okay. So here it is. No, just a second. Open share tray.
There is a button near microphone.
You hear me?
Yeah, we can hear you.
All right, you hear me, but I'm sorry, but yeah, I would like to put my screen on. if possible. So I open share tray.
Yes.
And so let me click on my presentation. Do you see it now?
Yeah, we can see it now.
Perfect. Very good.
Okay, let us start our next talk. I'm not sure that I will spell correct. Francis Golse.
Yes.
Okay. Okay. Partial regularity in time for the Landau equation. Please start.
Okay, thank you very much for your kind invitation to this meeting. I shall present some recent work with Maria Pia Gualdani from University of Texas at Austin, Cyril Imbert at École Normale Supérieure, and Alexis Vasseur also at UT Austin. All right, so the Landau equation is a variant of the Boltzmann equation in the kinetic theory of gases, which was proposed by Landau in the late 30s to model collisions involving charged particles, because if you write the collision integral, the Boltzmann collision integral in the case of Coulomb interaction potential, it simply doesn't make sense. So Landau came up with the right theory for describing collisions between charged particles. So the Landau equation usually involves an unknown, which is a distribution function, velocity distribution function, which is a function of time, space, and velocity, which is usually the number density of particles which at time t are located at the position x and depend on the velocity v. But for this talk, I'm going to focus on the space homogeneous Landau equation, meaning that I'm going to look exclusively at solutions of the Landau equation which are independent of the position variable. So here the unknown is going to be the distribution function f, which is a function of t and v only, a non-negative function which satisfies the equation written here. So del t of f for t and v is a divergence in v, so v is the velocity vector in R3. So dtf is the divergence in v, the integral over R3, the collision kernel, the Landau collision kernel A of v minus w, which is a matrix field applied to del v minus del w of f of tv, f of tw, and you integrate in W. So here I'm using the following notation for the collision kernel, A of V minus W. So A of Z is 1 over 8 pi the Hessian of the Euclidean norm of Z. So if you compute what it is, 1 over 8 pi the norm of Z times pi of Z, where pi of Z is the orthogonal projection on the plane orthogonal to the line spanned by the vector Z. So if you compute the integrals in W under the divergence here, it's fairly easy to write the Landau equation in this way, which goes by the name of non-conservative form of the Landau equation, which is del Tf or T and V, which is some diffusion matrix that's obtained by taking a convolution product of A with F. So what this gives you a matrix. In this matrix, you take its contraction with the Hessian of F, and you add F squared. Now, there is an obvious open question, which is a question of global existence of classical solution or finite time blower for the Cauchy problem for the Landau equation with prescribed initial data. Because, of course, if you look at this non-conservative form, you see immediately, for instance, that if F does not depend on the velocity variable, this reduces to a Riccati equation dtf equals f squared, which is known to blow up in finite time. However, here you're interested in distribution functions, meaning that you want typically that the integral of f dv be finite. And it's essentially impossible for that reason that f be dependent of v. However, if you look at this equation here, and if you really want to take into account the v dependence of f, which you should for physically meaningful solutions, then there's another model which you might think of, which is a semilinear heat equation. So if you look at the semilinear heat equation, there is indeed finite time blow-up if you look at non-negative solutions of delta u equals Laplacian u plus alpha u squared with positive alpha. And the way you prove this is also related to the Riccati equation, and it goes by the name, it's something rather old, it goes back to the 60s, it goes by the name of the Kaplan's method. So the idea is to write a Riccati inequality, L dot of t, time derivative of L, larger than or equal to minus lambda naught L of t plus alpha L of t squared, where L of t is this quantity here. So L of t is the average of the unknown function u with respect to the density, which is defined in this manner. So you look at the solution minus Laplacian phi equals lambda naught of phi, with phi positive on the unit ball, say, and with Dirichlet boundary condition at the boundary of the ball. So here, this eigenvalue equation, because you require phi to be positive on the ball, implies that lambda naught is going to be the ground state of the Laplacian, right? So then you take this phi and you compute L of t, you define L of t to be the average of u in the ball, with that for the probability measure proportional to phi, and you get this Riccati inequality, which again blows up in finite time. However, if you return to the Landau equation, you see that, of course, if f increases, then the diffusion, which is here, also increases, and therefore there might be a chance that this diffusion, this increasing diffusion, will ultimately offset the effect of the nonlinearity f squared, which is here. Right? This is an effect which, of course, you don't see in the semilinear heat equation because the diffusion here is simply a constant. So for this reason, people have looked at a variant of the Landau equation, which is known as the isotropic Landau equation. Namely, you look at this parabolic equation here. Del T of u equals minus Laplacian minus 1 of u times Laplacian of u plus alpha u squared. Well, for this model, you can prove global existence of radially symmetric, non-increasing solutions. And this has been done by Maria Gualdani and Nestor Gillen in 2016, with previous works by Philipp Gressmann, Joachim Krieger, and Bob Strain in 2012. All right, this is pretty much what is known for this isotropic Landau result. The best result is really this result by Gualdani and Gillen for the non-increasing radially symmetric solutions. If you want to look at the true Landau equation, there are also a conditional regularity result. This is the best one, probably by Silvestre, to the effect that if you look at L infinity in time with LP in V solutions with P larger than 3½ and sufficiently many moments controlled, you want 5 moments, then such solutions are going to be L infinity in time and velocity and therefore regular, right? Okay, so that's pretty much what we know. So the question of regularity for this problem is pretty much open. All right, so let me review briefly the formal properties of the Landau equation. So first, there is a conservation of mass, momentum, and energy, meaning that if you take F to be a solution to the Landau equation, you integrate F against any component of the vector V and the norm of V squared, then the resulting integral is going to be an invariant of the motion. In other words, del d by dt of the integral of F times 1v v squared v is equal to 0. There's another property which is called the H theorem by analogy with that property for the Boltzmann equation. It goes back to Boltzmann himself. So assume that f of tv is a positive function almost everywhere. Then you can prove that the time derivative of the integral of f log of f dv, so that's the analog of minus the entropy, right? And this is precisely the functional which Boltzmann called the H function. So in the case of the Landau equation, the time derivative of this quantity is equal to minus the integral in V and W of this non-local dissipation rate. So it's F of TV, TW divided by the norm of V minus W times the square norm of the orthogonal projection and the orthogonal of V minus W of del V of the log of F minus del W of the log of F, right? So which you can, if you prefer, you can also recast this term in this manner here, involving the square root of F of TV, F of TW, divided by the norm of V minus W. All right, so these are formal properties which have been known for a long time. However, if you want to prove the existence of a solution to the Landau equation, of course, you can use these properties. However, the precise result which you get, you don't exactly have these properties satisfied, right? Yeah, I mean, you have some variant of these properties. And then in 1998, Cédric Villani constructed global weak solutions with some of these additional properties which I showed you of the Landau equation. And the properties of his solutions, which he called H solution, after the Boltzmann H theorem, because the entropy plays a great role in this definition. So the properties are summarized here. So here, henceforth, I'm going to denote LPK. The LP norm of V was the weight corresponding to a moment of order K, right? So it's the LP norm of V with respect to the measure 1 plus V squared to the K over 2, or if you want 1 plus V to the K dV. Right, so here P is larger than or equal to 1, and K is any real number. K could be positive or negative, as you wish. All right, so H solution is going to be a non-negative function. It's continuous in time with values in distribution. It's going to be L1 locally in time with values in L1 with this negative weight, L1 with the 1 over 1 plus the normal V weight, satisfying the conservation of mass, momentum, and energy, satisfying the non-increase of, not the decay. The fact that the H function at time t is less or equal to its initial value. So this should be true almost everywhere for almost every positive time. And you want that for each test function, which is C1 with compact support in time and velocity. If you denote by capital phi, its gradient and velocity, you have the following relation. So here, let me just insist that if you write the definition, the standard definition of the solution, of being a solution in the sense of distributions, it's not exactly this which you would obtain. You would obtain something that would involve second derivatives of phi. Here, that's not what we're doing. What you're doing in this definition is you simply integrate once by parts in V, and of course in time also, so that this definition involves this capital F, which appears in the production rate of the H function in the form of H theorem. So in other words, this quantity here is known to be square integrable, and therefore the integral which is written here makes sense. The fact that this quantity is square integrable comes, of course, from this bound here and the formal form, the expression, the formal expression of the dissipation rate. Okay, very good. So now this dissipation rate is obviously a non-local quantity. If you look at it in this way, it's an obviously non-local integral operator because you have to integrate in dW, right? And it involves values of f at two different velocities. This is obviously a difficulty, but recently Devillet in 2015 proved a very nice result, which essentially amounts to having a control of this dissipation rate in terms of a local quantity, right? So this is a functional inequality to the effect that if you pick your favorite f, which is L1 with the weight v squared on R3, which is a finite H function, right? So this is a function of v only, and you're going to apply this functional inequality to each, to the solution to the Landau equation for each value of time. Then the integral of R3 of the gradient of the square root of f to the squared with the weight 1 plus the normal v to the cube dv. This is controlled by some constant that depends on the mass, momentum, energy, and entropy times 1 plus the entropy production rate of the Landau equation. So you see, this quantity up to this constant is bounded below by something that looks like the Fisher information. It's the L2 norm gradient of the square root of f up to this weight 1 plus, to this negative weight 1 plus v to the minus 3. Okay? As a result, one implication of this important theorem is that you can show propagation of moments for solutions, for the Wieland solutions of the Landau equation, right? So if you assume that your F initial is L1 as k moments, with k larger than 2, has finite entropy, then the Villani solutions, any Villani solution starting with this initial data will be L infinity in time with values in L1 with exactly the same number of moments, right? Very good. So the moments are going to be locally bounded in time. Okay, so now if you look at the Devillet theorem, it puts the Landau equation in the same class as 3D Navier-Stokes in terms of Lebesgue exponent, and the dictionary is explained here. So for Navier-Stokes, the Leray theory tells you that the velocity field is bounded in time with values in L2 in space, and the gradient of the velocity field is L2 in time and space. For the Landau equation, the square root of f is going to be, again, L infinity in time with values in L2 in V. This is the conservation of mass, say. And de Villette theorem tells you that the gradient of the square root of f is going to be L2 in time and space. However, there is this negative weight, 1 over V to the cube. But apart from this negative weight, you see that the Lebesgue exponents are pretty much the same. Now, for 3D Navier-Stokes, Leray proved in 1934 not only the existence of weak solutions, but also the fact that the set of singular times of these weak, so-called turbulent solutions has one-dimensional Hausdorff measure equal to 0. So there's a natural question, which is, what is the maximum Hausdorff dimension of the set of singular times for a weak solution of the Landau equation? Good. So here I flash before your eyes the definition of Hausdorff dimension, which, well, I mean, I'm sure that everyone knows. You cover the set whose Hausdorff measure you want to compute by sets of diameter at most delta. You take the sum of the diameters to the power r, and you take the sup in delta of the inf of all these covers that defines a measure on the Borel sigma algebra of your metric space, and you define the Hausdorff dimension as the infimum of the exponent, such that the r-dimensional Hausdorff measure of your set is equal to 0. And with this definition, you can check the Hausdorff dimension of the middle third contour set, for instance, is going to be log 2 over log 3. This is an elementary exercise. Good. Now, there is an object which I'm going to play with, which is a notion of truncated entropy. So so far I've introduced the entropy, the Boltzmann H function. So the truncated entropy is defined in this way. You look at the function h plus of z to be z times the positive part of the log of z minus the positive part of z minus 1. So if you draw h plus, this is the function which is equal to z log z minus 1 for z larger than 1 and equal to 0 for z less than 1. Right? And with this, I'm going to look at h plus of g at the level kappa to be the integral of kappa h plus of g of v over kappa dv. Right? So that's my notion of truncated entropy. Now, there is a variant of the H theorem, which was our starting point, which was the first computation that we did to study the Landau equation, which is summarized on this slide. So turns out that, of course, if you do a time derivative of the H function, we've seen that this is going to be a negative function, this is a negative quantity. So what about taking the time derivative of the truncated entropy, and if you truncate the function at some level kappa? Well, the answer to this is given on this slide, right? So the time derivative of h plus involves a non-local integral, which is very much the same as in the H theorem, the standard H theorem, right? So you have the same non-local weight, f of tv, f tw over v minus w in norm. You have the square norm of the projection, but here it's the gradient of the log of f, where f is larger than kappa, minus the gradient of the log of f in w, where f is larger than kappa, which appears, right? And of course, there are terms which are going to mix places where f is larger than kappa at the velocity v, say, and places where f of w is going to be less than kappa. And if you compute carefully these terms, what you end up with is some interesting term, which is kappa times the integral of f minus kappa plus dv. Now, this is interesting and interesting. I mean, this is favorable. We call that a depleted nonlinearity, because if you return to the non-conservative form of Landau, which I'm going to show again here, you see that if you multiply both sides of this equality here by the log plus of f over kappa, then you will have here something that's going to be like f squared times the log plus of f over kappa, and therefore has a larger growth for large f than this term here, because this term here is grows linearly for f larger than kappa, not like an f squared log of f, right? So it's much less nonlinear, just because some parts of this nonlinearity have disappeared because of the special structure of the collision integral, the Landau collision integrals. There are some cancellations which result in this favorable term with this depleted nonlinearity. Good. So what can we do with this? Well, first we define a notion of suitable solution. What I mean by that is that if you look at the process by which Villani constructed his weak solutions, his what he called the H solutions, the very same process, we should call them Villani solutions if you want, with the very same process, you can, if you're a little more careful, retain some properties which Villani did not need and therefore which he neglected to keep at the end of his process. So there is this definition of suitable solution, which of course the idea of this definition is to have a rigorous formulation of this computation here, at least at the level of Villani solutions, right? So a suitable solution depends on some negligible subset of the time axis, depends on some Lebesgue exponent and some dissipation constant C. And it's such that if you pick any time t1 less than t2 not belonging to your negligible set, then the truncated entropy at time t2 plus some dissipation term, which I'm going to describe in a minute, is less than or equal to the truncated entropy at time t1 at the same level, plus your depleted nonlinear term, 2 kappa, the integral from t1 to t2 of the integral of f minus kappa plus dv dt. And here you have replaced so normally here you should have the David term that should be the Fisher information of f weighted with the negative 1 plus v cube weight. But here you get rid of the 1 plus v cube term weight, negative weight, by means of lowering the Lebesgue exponent, which is here. And using the propagational moments, right? I say if you do this, you lose a little bit on the Lebesgue exponent, which is here. You get a 1 over q there. And then you replace this Fisher information with these negative weights with something that does not involve any weight in the velocity v. It's an honest LQ norm with no weight in v. Right, the result is that if you assume that if you pick any f initial which has k moments and finite entropy for some k larger than 3, then there exists such a suitable solution of the Landau equation. And here, the Lebesgue exponent q is 2k over k plus 3. So observe, as announced, that the q is less than 2, right? Again, this is because I've traded part of this Lebesgue exponent for the moments, which I know how to propagate by the David theorem. Good. So now let me come to the main theorem that we proved. So we're going to call the regular time of a suitable solution of f on some interval a time tau belonging to the interval such that f is going to be L infinity on the strip tau minus epsilon tau cross R3. So for all velocities, for times between tau minus epsilon and tau, for some positive epsilon, of course, so that tau minus epsilon is positive, right? So that's a regular time, and you call the set of singular times of f, that is not regular times, the other times, if you want, you denote it by s of f on the time interval I, right? And the result is that if you take any suitable solution to the Landau equation on pick your favorite time interval, 0t cross R3 for all positive time, with initial data having finite kth order moments, finite entropy, finite mass, of course, for all k larger than 3, then the Hausdorff dimension of the set of singular times of f on the time axis is at most 1/2. All right, so let me briefly explain how this is going to work. So the proof of proposition 1, I'm going to skip it in interest of time. As I said, you pretty much take the proof of Villani and you follow all the arguments and you prove that the quantities which you're interested in pass to the limit and give you the control which I announced. So this is technical and not very much interesting. So the first idea in this business is to use the Georgi ID for the 17th Hilbert problem to prove a local bound. So here's how it works. So take f to be a suitable solution to the Landau equation, say for time in 0, 1, for some constant, ellipticity constant CE, positive, and here I'm going to take the Lebesgue exponent. For this argument, I need the Lebesgue exponent to be between 6/5 and 2. So, there will be several intermediate results where I might reduce the set of Q's corresponding to my suitable solutions. But what is important that these intervals of Lebesgue exponents should approach 2, right? So then, given this thing, there exists an eta naught which depends only on the Lebesgue exponent Q and on CE, such that if you look at the integral between 1/8 and 1 of the truncated entropy of the solution at the level 1/2, and if this quantity is less than eta naught, then f of TV is going to be less than or equal to 2 on a slightly smaller time interval. Specifically, it's going to be less than or equal to 2 almost everywhere on 1/2 1 cross R3. And again, I repeat that this eta naught depends only on Q and on CE. Obviously does not depend on the solution, right? So that's the first observation. And now, of course, the way this is done is by a standard the Georgi, Nash, Moser, whatever iteration involving an exponentially converging sequence of times, exponentially converging sequence of levels. You look at the quantity that involves f truncated at the level k, the level kappa k, excuse me, and the dissipation of that same quantity, right? So for this quantity here, then you prove that it satisfies some nonlinear inequality of form ak plus 1 less than or equal to some constant. Then there is a constant lambda, possibly larger than 1. So this is exponentially diverging. But here, this is multiplied by ak to the beta, where beta is larger than 1. And so the idea is that if A naught is small enough, the nonlinearity here is going to kill the exponential growth of the lambda. So that's the standard de Giorgi argument. However, this in itself is not enough to conclude, and you need to have a criterion for regularity that is going to be an additive, that's going to involve an additive set function. And so here is how it goes. So we call that an improved Giorgi type lemma, although this is not exactly in the this type of argument does not really appear in the original de Giorgi paper, right? So anyway, so here's the criterion. So suppose that you have a suitable solution to the Landau equation, again on 0, 1, say, with Q here, Q has to be larger than 4/3, and of course less than 2, right? So then you can find some eta 1 that again depends only on Q and CE, which is a positive threshold, such that, and there's this positive threshold, and there is a parameter delta 1 in 0, 1, such that if you assume that this quantity here is less than eta 1, then F is going to be bounded on the strip 1 minus delta 1, 1 cross R3. So what is this quantity here? If you look at it, this is the dissipation integral of F, right? Where I've replaced the, I've traded the negative weight in V for a lesser Lebesgue exponent, right? So the Q is less than 2 here. So I have an LQ norm with Q less than 2. And here F is larger than epsilon to the minus gamma, right? So F is large. You integrate between 1 minus epsilon to the gamma and 1. So this is a small time interval. And you look at the lim sup of this quantity scaled by an epsilon to the gamma minus 3. Right, so here, this thing is a large prefactor, right? So you want this thing to be less than eta 1. So, of course, here, the fact that this is large compensates the fact that the time interval here is small, right? So here, gamma is related to your Lebesgue exponent by this formula. Gamma equals 5q minus 6 divided by 2q minus 2. So the way this is done is by sorry, what's going here? Yeah. Yeah. Yeah, let me see. Let me switch that off. Right. Oh, I'm sorry, I don't have control on my screen. Yeah. Sorry. Oh, here it is. All right. So I'm not going to give you the proof in proposition 3, which follows essentially the same type of argument as the Giorgi argument, except that here, instead of looking at the values, instead of looking at iterating on the size of the values of F, we are also zooming by using the invariance properties of the Landau equation, which is known to be, which has an invariance group in the sense that if F of TV is a solution of Landau, epsilon squared of epsilon squared T, and epsilon V also is a solution. So you use these, the zooming on the function with the invariance group to get this result. Now with this, you can easily prove the main theorem in the following manner. You use proposition 1 to prove that F initial launches a suitable solution with some constant, some ellipticity constant. So this is for each Q in 1, 2, say. And suppose that tau is a singular time, you want to apply this proposition 3 to f of t plus tau minus 1 in v. And so because this is a singular time, it means that the regularity criterion, which is here, has to be violated. So in other words, it means that there must exist some epsilon that depends on tau, say between 1 and 1/2, such that the time integral between tau minus epsilon tau to the gamma and tau of the gradient of 1 over q minus which you raise to the power q, you're integrating dv, you take this to the power 2 over q, you're integrating time, that has to be larger than, say, 1/2 of eta 1 epsilon tau to the 3 minus gamma. Then you apply Vitali's covering theorem. Vitali's covering theorem tells you that there is a sequence tau j of singular times such that your set of singular times is going to be covered by intervals, time intervals of the form tau j minus 5 epsilon to the gamma, tau j plus 5 epsilon to the gamma. And if you shrink these intervals by dividing their length by 5, the resulting intervals are pairwise disjoint. Okay, and with this, you immediately see that 1/2 of eta 1 times the sum of the epsilon to the 3 minus gamma, that comes from the right-hand side of this inequality here. This, if you take the sum of this thing, adds up to something which is controlled by the dissipation of f and is therefore finite, right? But this gives you an estimate of some Hausdorff measure of your singular set, because gamma is equal to 5q minus 6 over 2q minus 2. Then you have this 3 minus gamma over gamma, which is q over 5q minus 6, and this inequality tells you that the q over 5q minus 6 Hausdorff dimensional measure of the set of the singular times of f is finite, and this is true for each q between 4/3 and 2. And if you let q tend to 2, then you discover that the 1/2 that the Hausdorff dimension of the set of singular times is at most 1/2. Now, well, this is pretty much the end of the proof, and so let me conclude with final remarks and maybe perspectives. So here we've looked at the Hausdorff dimension of the set of singular times for the equation. So it would be actually interesting and probably more precise to look at the Hausdorff dimension of the set of singular time and velocities in in space, in time and in the time and velocity space, in 0, infinity, cross R3. So can one find an upper bound for this? We have an answer so far, which is not very satisfying because we find that this Hausdorff dimension is less than or equal to 7/2. Not very satisfying because 7/2 is not very different from 4, but that's the best we could do at the moment. However, we have two, with the same method, we're able to prove perhaps more interesting results to the fact that radial Villani solutions of Landau Coulomb, we're able to prove that they're locally bounded and they're regular away from the origin in velocity. So they're locally bounded and 0 infinity equals R3 minus the origin. And axis-symmetric Villani solutions of Landau Coulomb are locally bounded for all times cross R3 minus the axis of symmetry. So this we have a recent preprint on arXiv for these three results. Now, of course, this is for the Coulomb case, which is the most important for physical applications. But there's also the question of global existence of a classical solution for the maybe easier case where the collision kernel A of z is pi of z divided by z to the gamma, with gamma between 0 and 1. Physically, probably less interesting, but it's a mathematical problem which is still open. and will be certainly good to be able to solve it. So with that, I'm going to stop, and thank you for your attention.
Okay, let us thank the speaker. Now, what are the questions, remarks? Okay.
Thank you very much, Francois, for a very interesting.
Thank you. My pleasure.
For a very interesting lecture. I am interested in the following. When you speak that it is maybe possible or more easier to solve Landau equation for not for Coulomb case, what do you mean? As far as I know, Landau equation is a partial case of Boltzmann equation for some functions, and perhaps it is more easier even for rigid spheres to Landau approximation for rigid sphere to try to prove these theorems, and this is such a complex of questions.
Oh yes. Yes. Indeed. Maybe I should mention this. Hard spheres, as you were asking, hard spheres belong to a class of potential. I think for hard potentials, regularity has been proved. It's already known. I think regularity, the fact that Landau solutions are regular is unknown for any potential such that the kernel A of V minus W decays at infinity. So if because the point is that you start. You lose ellipticity, right? Because you have the diffusion. I mean, A of V minus W. The fact that it decays at infinity implies that you don't have a lower bound for the diffusion constant. And because of this. This is where it's difficult. If you know that A of V minus W is bounded from below, then the regularity is not an issue. It's known. It's known that such solutions are regular. Yes.
Okay. Other questions? Okay, let us thank again the speaker.
Thank you very much.
And we, it's lunchtime now, and we meet at 10 after the lunch.
Okay, have a good day.
Коллеги, если вы собираетесь на ланч в столовую РУДН, она будет работать сегодня до 3, поэтому поторопитесь, пожалуйста, да, к сожалению.